Good morning and welcome to this the lecture number 37 of the course Stochastic Hydrology. Now, we are discussing some practical aspects of the data analysis. All the techniques that we have studied earlier deal with the observed data, and when we have observed data let us say of the stream gauges, we need to do certain checks to make sure that the data that we are using for the analysis is in fact of good quality, it is consistent, and that we can use this data in our analysis to make some decisions. In fact, why we do all this analysis is finally to make decisions on the hydrologic designs, let us say of the reservoirs or reservoir operating policies, or even hydrologic designs such as the capacity of the weirs that we want to provide, the culverts that we would like to provide at certain locations, and so on. So, the analysis is essentially done to make sure that finally, the designs that we make, the engineering designs that we make are representative of the data that we have observed. And therefore, in the last class I introduced what are called as the consistency checks for the data. That means, once we have observed data at several locations, stream gauges and so on, we need to check whether the data series that we have for analysis is in fact consistent with the data series that is available elsewhere at other gauges in the same catchment or in the surrounding catchments and so on. So, essentially we look at the homogeneity as well as the consistency of the data. In the last lecture, we examined typically the methods for data filling. Let us say that you have observed data at a particular location for 50 years and something, and in this 50-year sequence of data, in the 50-year series of data, there may be many values missing for several reasons. Maybe it has been not observed, or it has been faded in the sense that they would have recorded on paper and then for some reason it has faded and you are unable to make out exactly what is the data, or the gauge may not be working during those periods and therefore, there is no data available and so on. Typically, whenever we have hydrologic time series, especially in the developing countries like ours, we may not have continuous records. There may be certain values that are missing, and it is important for our analysis to have a continuous time series of data, and therefore, we adopt the procedures that I discussed for missing of the data, filling of the missing data. If you recall, we look at the dates on which the data is missing and then simply fill it by the mean of the flow. If we are talking about the flow data, mean of the flow for that particular day, using all the remaining years of the data in which data is available for that particular day, calculate the mean of that and then simply fill it. This is the simplest way, and I have also introduced some other more rigorous ways of filling the data in the last lecture. We typically used two different periods. For example, monsoon period we adopt certain procedure, non-monsoon period where the flows are very small in the peninsular region, where the flows are very small in the non-monsoon period, essentially due to the flows are essentially due to the base flow during the non-monsoon period. So, we adopt different procedures for the monsoon periods as well as non-monsoon periods for filling up the data. Once we have filled the data and now we have a continuous time series available at a particular gauge, in fact, at all the gauges that we are interested in that particular catchment, then we start the consistency checks. In the consistency checks, we ask the question, yes, we have this time series, how representative is this time series with respect to the time series that are observed in the other locations of the same catchment. So, that is where we do the consistency checks. And like I have been mentioning all through the course, the first thing that we do is whenever you have data, plot the time series first of the data and then do the statistical analysis. Simply look at the mean, standard deviation, coefficient of variation, and then you look at the skewness coefficient and so on. Simply get the statistics of the data. The statistics of the data is telling you the story of what has happened at that particular location, how variable the flows are, what is the maximum flow that you can expect, what is the minimum flow that you can expect, what is the mean flow for a long period of time and so on. So, this is we have to keep this in mind when we are doing the analysis using the stochastic hydrology methods. We have to keep in mind that we are relying all our decisions on the data that has been observed, and the data that has been observed at a particular location in fact tells us what has happened at that particular location. It tells us the story of the processes that have happened there, and therefore, we must respect the data, observe data. At the same time, we must make allowance for the errors in the data collection, errors in the data itself, the non-reliability of the data, the bad quality of the data. We have to make allowance for all of these. We must have some rigorous methods of doing all of the making allowances for all of these and then use the data. This is an important aspect, and therefore, I keep on stressing this, because in practical applications simply we pick up some data that is provided by the agencies or the custodians of the data and then start analyzing. The first thing is you suspect the data, whether the data is of good quality, the data is reliable and so on, and therefore, it is important for us to make rigorous checks on the data that we have obtained with respect to the data that is available elsewhere, and then may proceed with the analysis. The consistency checks that I introduced in the last lecture are typically looking at a particular gauge. Let us say that we have two gauges, this is a stream flow, and then there are two gauges, let us say gauge A and gauge B, and the flow direction is like this. So, if you want to check the consistency of this, remember the flows that are recorded at the site B are the flows that are contributed by the upstream catchment up to this point, and the flows that are recorded at gauge A includes the flows that are recorded at gauge B, and therefore, it will have this particular catchment. So, the flows at A must be greater than or equal to the flows at B, and typically they will be this flow plus all the intermediate catchment flow that has not been recorded by the flow B, flows at B. So, typically this is the intermediate catchment flow that comes in and therefore, if you plot a let us say double mass curve, in the sense that flows at this location with respect to the total aggregated flows that have been recorded at B, you must expect a straight line, and typically the flows at A will be the cumulative flows at A as time progresses will be greater than the cumulative flows at B. So, this is one analysis that we do. I will demonstrate this with a particular case study. Now, if that does not happen, what does that mean? Let us say that the flows at A, I represent it as y A, is should be greater than or equal to let us say y B, if I represent y as the flow. If it does not happen, that means if y A is not greater than or equal to y B, what does that mean? It either means that there is something wrong with the data that we have observed at A, or it may mean that you are using a lot of water between B and A, and this is going either as losses or for utilization. Let us say that you have a major lift irrigation scheme between B and A, and then you are continuously using the water at that point, and then the intermediate catchment is not contributing enough to account for the utilization. Then it is possible that the flows at A are not in fact equal to in fact greater than or equal to flows at B. if this is not the case, or if you are not able to account for why the flows, the fact that the flows at A are not greater than or equal to the flows at B, it means that there is something wrong with either our recording or our way of measurement itself, and therefore, you must suspect the inconsistency in the data. The other part that I mentioned in the last class is what are called as a specific flows. Now, this is a concept that we often use in India for checking the consistency when we are talking about large water resource systems. Let us say you are talking about a catchment of the size of Narmada river basin or Mahanadi river basin, lakhs of square kilometers of the area, in which you will have sub catchments which will which may all be considered as hydrologically homogeneous regions, in as much as the way they respond to rainfall in terms of the runoff generation. These characteristics are the same across the sub basins, and therefore, these sub basins can be treated as hydrologically homogeneous. If a catchment is hydrologically homogeneous, it means that the specific flow or the flow per unit area that you get for a particular rainfall must be the same across different subcatchments. If let us say subcatchment A and subcatchment B are hydrologically homogeneous, it means that the flow generation characteristics of the catchment are the same for both these catchments, and therefore, the specific flow, which is the flow per unit area, must be the same for both these catchments, and that is what we check in the consistency. So, with this now we will progress and then look at some examples of what we mean by consistency of the data with respect to the mass curve as well as with respect to the specific flows. The specific flow is expressed as flow volume per unit area of the catchment. So, simply look at, let us say a particular gauge, it has recorded a certain flow, and you look at the annual average flow, let us say, and divide it by the catchment area. That will give you the flow volume per unit area of the catchment, and therefore, it will be typically in the depth unit or cubic meters, million cubic meters per square kilometer of the area. In that area, in those units, the specific flow is expressed. Now, as I said, the specific flow is in fact representative of the catchment's response to precipitation. There is a precipitation occurring, how much of this precipitation gets converted into runoff is what is given by the specific flow. So, it is in fact the response of the catchment to an input that you are providing, hydrologic response. Now, if a number of gauge stations are located in the same hydroclimatic region, as I said, hydrologically homogeneous regions, then you must expect that the specific flows are comparable. This again I have told in the last class, but because it is an important concept, let us again recall this, what I mean by that. Let us say that you have two regions like this. There is one catchment here, the flows are taking place here, and then you have recorded the flows here at this point A, and this is a catchment that is contributing to the flows at bay A, and then there is another hydrologically homogeneous region to this catchment, and you have recorded the flows at B. These two are different catchments. Now, if these are hydrologically homogeneous in the sense that their responses are the same to a given precipitation, then the specific flow at B, which is the average flow divided by the total area of this catchment, must be comparable to the specific flow at A, which is the average flow that is recorded at this location with respect to the catchment area divided by the catchment area. Now, typically we do this when we are analyzing large water resource systems, where there is one gauge here and there is another gauge here, and maybe perhaps you have another gauge here like this, and the flow directions are like this. Let us say this is the flow direction. Now, we compute the specific flow at this location with respect to the catchment area of this particular gauge. Similarly, we compute the specific flow of this with respect to the catchment area of this gauge. Let us say we call it as A, B and C. Now, the C will comprise of this entire area. These borders are coinciding here. So, C will measure, the gauge C will measure everything that is measured at B, everything that is measured at A, plus the intermediate catchment flow between these locations. Now, when we compute the specific flow at B, we take the flows at this and take this area and compute the specific flow at B. Similarly, specific flow at A and specific flow at C. The areas are different and so are the flows at all of these locations, but the ratio of the flows to the areas will be approximately the same if they are hydrologically homogeneous, which means that the precipitation pattern is the same in all the three catchments, as well as the land use patterns are the same, the vegetation is the same, the amount of urbanization that has taken place in these catchments is the same, the type of soils is the same. In other words, the complete gamut of the hydrologic variables that contribute to runoff generation are the same for all these catchments, in which case the response of these catchments will be the same for a given precipitation pattern, and then we say that these are hydrologically homogeneous catchments. If they are in fact hydrologically homogeneous catchments, then the specific flow that we compute at this location must be the same or must be comparable. Ideally, it must be the same as this, but at least it must be comparable to the specific flows computed at these locations. Let us say that the specific flow computed at C is much higher compared to the specific flows at A and B. Let us assume for the time being that the specific flow at A and specific flow at B are comparable, and therefore, there is a good reason to believe that the precipitation patterns and the hydrologic responses of these two catchments are similar. However, the specific flow at C, which represents this entire area, and typically it accounts for this intermediate catchment area, which is not covered by both this A and B. If that specific flow is much higher compared to the specific flow at A and B, what does that mean? It means that the intermediate catchment here, let us say that I show this by some, let us say all of this has been the intermediate catchment flow. In fact, these two are adjoining with each other, the entire flows are captured by A and B. Now, if the specific flows at C are much higher compared to the specific flows at A and B, it means one of the two things. It may mean that the precipitation pattern here, the precipitation values are much higher in this intermediate catchment compared to the precipitation patterns here, and therefore, for the same hydrologic characteristics of the region, you are getting more flows at this location, more observed flows at this location. Or it may also mean that the precipitation patterns may be the same, but your catchment characteristics are such that for the same given precipitation, it is producing a higher inflow, higher flow at this location. If your recorded data is correct, then it means one of these two things. One is that the precipitation values are much higher here, or that the hydrologic characteristics are much different compared to these other two catchments, and therefore, it points to a non-homogeneity of this catchment compared to the other two catchments. So, these are the tests that we need to do for checking the homogeneity and the consistency of the data at that particular location. So, we will go back to the example and then see how these values look. Now, we compute the annual specific flows. Typically, when we are doing large scale systems analysis, water resource systems analysis, we look at the annual flows and then compute the specific flows. So, let us say 50 years of data is available, annual data is available. You take the annual average flow and then divide it by the area of the catchment, you get the annual specific flow. This can also be done for seasonal flows. Let us say one season, monsoon season and non-monsoon season, you can compute the specific flows. Now, as I have been mentioning, the specific flow is useful in comparing the runoff per unit area from different sub catchments within the larger catchment. And the units are typically million cubic meter per square kilometer. This is a measure of the annual average runoff in depth units, typically in meters or centimeters or some such thing. The example that I have been showing in the last class, this was I was talking about Narmada river basin. This example has the average annual rainfall varying between 700 millimeter to about 1650 millimeters. As you go from east to west, the rainfall is varying significantly. And therefore, for large river basins, as the rainfall patterns are changing, if your hydrologic responses are the same, then you may expect different specific flows for different sub catchments. Let us see how it looks like. So, this is a system view. It may not be very clear, but do not worry about it. It only shows there are large number of gauges, stream gauges. These rectangles here, small rectangles, they are stream gauges. And this is the Narmada river. This is Amarkantak here at this point, and this is the Bargi reservoir here. Then there is Indira Sagar reservoir here. There is Maheshwar reservoir here. There is Sardar Sarovar reservoir here, and so on. And there are large number of gauges, in fact 55 number of gauges at which the flows are recorded on all of these. The available record at these gauges varies from as few as 5 years to the length of the record varies from as few as 5 years to as high as about 40 years, 50 years and so on at several locations. And we have to make use of this data to arrive at decisions. Let us say that you wanted to put another reservoir somewhere here, or let us say that there is an ongoing reservoir for which you want to develop operating policies, in which case you have to analyze how the flow pattern has been at that location. And therefore, it is important for us to check. Let us say for Maheshwar reservoir, there is a gauge Mandleshwar. Now, the Mandleshwar gauge at this location, if I slightly zoom that or draw a zoomed picture here, this is Mandleshwar at this location, and then there is another gauge here. This is Mortakka and this is Maheshwar, that is Mandleshwar, which contributes to Maheshwar reservoir. And then there is also another small stream that is coming here, and there is a gauge called Kogaon. So, just focus on this Mandleshwar gauge now. Now, this has a intermediate catchment between Mandleshwar and Mortakka, between this a very small intermediate catchment, and also between Kogaon and Mandleshwar. So, we look at the catchments for Mandleshwar, catchment at Mortaka, catchment at Kogaon, and compute the specific flows. And because they are quite close to each other, because they belong to the same sub catchment, and if we can reasonably assume that there is hydrologic homogeneity in terms of the response of the catchment sub catchments, then the specific flows at these locations must be comparable. Similarly, you look at let us say Sardar Sarovar reservoir. Near Sardar Sarovar reservoir, just upstream of that, there is a Rajghat, which is a stream gauge. Then there is also Tikola, which is coming from the side here, and then immediately downstream of that there is a Garudeshwar stream gauge. So, you will have records before this reservoir came up, you will have records in Garudeshwar, and then you also have records after the flow has been obstructed by Sardar Sarovar reservoir. We will see what is to be done with the reservoirs and how to compute the normalized flows subsequently. But assume that you have normalized flows. By normalized flow, I mean that the effect of the reservoir has been taken out and the flows have been converted into naturalized flow series. So, if you have flows at this location, flows at this location and flows at this location, you can examine the consistency of the data of Garudeshwar with respect to Tikola as well as with respect to Rajghat. So, you check the consistency with respect to each other, and then you will be able to point out whether the data at a particular location is in fact inconsistent with respect to the data at other locations. We will not be able to say for sure whether this data is correct or that data is correct, but let us say that you have a large number of gauges like this and all of them, many of them are consistent with each other, but one of them is inconsistent. Definitely, we will be able to point out that there is something wrong with the data that is observed at this particular location. All right. So, when we do that, as I mentioned, for every gauge that we have, let us say Dindori, Manot, Mandla town, etc., you will have the catchment area. Now, all these different gauges are pointed out or put here, are shown here. This is Handia, for example, this is Hoshangabad, and then this is Jamtara, and this is Manot gauge, and Hridayanagar, and so on. So, all these at all these gauges we have the catchments which are contributing to the flows that are recorded at those particular gauges. So, these are the gauge sites and these are the catchments. So, for some places you may not have the catchment available and also the duration is very small, and therefore, you can ignore those stations. So, the catchment area is given here in square kilometers, and then you calculate the annual specific flow million cubic meters per square kilometer. The annual specific flow is computed based on the annual average flow recorded at that particular gauge site divided by the catchment area, which is contributing to flows at that particular gauge. So, these are the values that you get 0.546, 0.659 and so on, like this. These are the values that you get. Similarly, for several sites, we have chosen 30 sites here in this particular case. All the 30 sites we compute the annual specific flows. So, the first step is simply calculate annual specific flows, and then also look at the monsoon specific flows or the seasonal specific flows for monsoon period. So, I have also shown here the seasonal specific flows. Look at these values. The seasonal specific flows must be smaller than the annual specific flow, because you are taking the total volume of flow that has happened, that has occurred during the entire year in the annual specific flow, and the total volume of flow that has happened or occurred during the monsoon season, which will be smaller than the flows in the annual scale, and therefore, the seasonal specific flows will be smaller than the annual specific flows. Like this, we compute for all the 30 gauge sites the specific flows wherever it is possible, where the data is either very small or the catchment area or some other data is not available, we do not include that. Then the next step is we plot what are called as a flow duration curve. Remember, all of this we are doing to examine whether the data that we have for our analysis purposes is good to use, or is there any difficulty in is there any problem with respect to some gauges, in which case those gauges we have to discard in our analysis. The flow duration curves, which is also an important step in hydrology, construction of flow duration curves is an important step in hydrology. These indicate, let us say that a particular series we have, let us say we have the observed time series y t, these are flows and we are talking about monthly flows, let us say monthly flows, t is equal to 1, 2 etcetera. If you have 50 years data, we may have 50 into 12, that is 600 values. So, this is the time series of monthly flows that we have like this, okay. And this has a long term average of this and so on. Now, the flow duration curves indicate the percent of values of flows. Let us say we are saying here probability of x being greater than equal to x is equal to, let us say 0.5. What does this mean? We are saying with 50% probability this flow value x will be exceeded, that is the flow, let us say this flow is 500. So, the flow stream flow x will exceed a value of 500 with a probability of 0.5. Similarly, if I increase this 0.7 to 0.7, what happens? This flow magnitude will decrease. So, probability that the flow will exceed, let us say 700 units will be equal to 0.7 and so on. So, the flow duration curves give this trade off between the probability of exceedance and the magnitude of the flow. How do we compute? We simply use, let us say either the Weibull's formula or something, you arrange them in rank, decreasing orders, assign ranks and then give the percentage of exceedance and plot the percentage of exceedance with the flow magnitude. That is how you obtain the flow duration curves. If you are not using Weibull's formula, let us say, which is m divided by n plus 1 for getting the probabilities, you can simply get the fraction of flows that will be exceeded. Simply take it as arrange them in decreasing order. Let us say you have 600 values, arrange them in decreasing order and then assign this as 100%, the lowest value as 100% exceedance, because the minimum value will be exceeded 100% of the time in the record, and this come to about it has to be actually 0%, but as I mentioned in dealing with our probability plotting positions, that you should not assign a 0% or the 100%, you go as close to 0% as possible and as close to 100% as possible in this, and that is why we use typically m divided by n plus 1 as plotting position for the probabilities, estimation of probabilities. So, we use this kind of assignment of probabilities to each of these flows here and then plot the flow duration curves. Let us see how the flow duration curves look like. So, at different locations we have the flow duration curves like this. At any given value here, this is the x axis is percentage time equaled or exceeded. Let us say you have 70%, you get a flow of the order of this is 10, this will be 11, that is 100,000, this is 110,000, this is flow in million cubic meter. Like this, it indicates the flow that will be equaled or exceeded 50% of time, if you are looking at this location, 60% of time and so on. So, the flow duration curve gives an important information for design purposes. For example, at Mortek also you have 70%, you have slightly higher flow, this is 100,000 here, this is also 100,000 here. So, 60% you have 110,000, 120,000 and so on. So, compare these with respect to each other for the same given percentage, what is the flow that is exceeded at various locations. If Mortaka is downstream of Hoshangabad, then for the same given percentage you must have a larger flow. Similarly, if Garudeshwar is downstream of Mortaka, for the same given percentage you must have a larger flow and so on. Then we do the data consistency checks. Now, this is a large river basin that we are considering, and therefore, we do the data consistency for sets of gauges. We look at a particular gauge with respect to its immediate upstream gauge, its immediate surrounding gauges, and if there is a reservoir, we also look at the reservoir flow with respect to the immediate surrounding gauges. So, the types of consistency that we do for the data are first consistency of flow data at a gauge site with the sum of flows from immediate upstream gauges. Like I said that you have a gauge here, you may have an immediate upstream gauge on the same catchment, or you may also have certain gauge flows that are coming from tributaries. Let us say there is a tributary here, you have a gauge here, and there is a main stream, you have a gauge here and so on. So, when you are checking the consistency at this location A, you must look at what has happened at this particular gauge, as well as at this particular gauge. So, you are looking at immediate upstream gauges. However, if you have another gauge that has contributed to this flow, that gauge you do not have to worry, because that has been already recorded, the flows at that gauge has already been recorded by this particular gauge, and therefore, you look at immediate upstream gauges for this particular gauge. So, we check the consistency of flow data at a particular gauge with the sum of flows from immediate upstream gauges. That means, something is being contributed here, something is being contributed from here, something is being contributed from here. You add all of them up, or you look at the sum of these and then look at the consistency of the data. Then we also look at the consistency of the flow data with respect to the specific flows. As I mentioned, you look at the catchment areas of each of these gauges and then see the consistency with respect to the specific flows. Then we look at the consistency of flow data with the flow data at an immediate neighboring upstream station. That means, the data at this point must be consistent with this individually, it must be consistent with this individually, it must be consistent with this individually. So, one at a time also you look at. In the first step we considered all of these together and then looked at the sum of the data. Then it must be also consistent with individual gauges, stream gauges. Remember here the underlying assumption is that all these gauges belong to a hydrologically homogeneous region. The precipitation pattern is the same and the catchment response is the same at all of these locations. If those are not there, then it will not be consistent. Then we also check consistency of the reservoir inflow data where available with the data from the surrounding gauges. Let us say that around this point immediately upstream of this you have, let us say, a reservoir here, and you have the reservoir levels. Typically, whenever you have a reservoir site, reservoir levels will be measured, and therefore, you have the flow or the inflow data to the reservoir, that is data on the inflow to the reservoir you will have. Now, those should also be consistent with the data that you have observed at these locations. If you are downstream of a reservoir, then you have to account for the effect of this reservoir in terms of the controlled flows and then look at the consistency of this. Then we first start with homogeneity and consistency with respect to immediate upstream gauge. So, first we look at only two gauges now, that is a gauge A with respect to immediate upstream gauge B, and plot the double mass curve. That means, accumulated flows at this location with respect to the accumulated flows at this location. If there are more gauges that are coming from tributaries and so on, you also consider those gauges. Then we plot a double mask curve between accumulated monthly flows at the site being examined, which is A in this case, and the accumulated sum of monthly flows at all these upstream gauges. So, that will give you a double mask curve, as I will show you now. Then let us say that the double mask curve that you plot okay, let me make that slightly more clear now. What do I mean by the double mask curve? That you have two gauges, let us say this is gauge A and you have another gauge B and another gauge C here, and this is the flow direction, this is the flow direction here, and you are examining now the consistency at gauge A. And B and C, that is the flow at B and flow at C, have contributed to flow at A along with the flow in the intermediate catchment. So, when you plot the double mask curve, what you will do is you will take in some sense, in fact, you will take the sum of the flows at B and flows at C and then plot the cumulative flows or the sum of flows at B and C with respect to the sum of flows at A. This is a cumulative flow picture, and therefore, it will be continuously increasing. Let us say that you get a some such curve here. Actually, it should be a straight line, as I mentioned. If it is perfectly consistent, it will be a straight line. Now, if you draw a 45 degrees line here, this curve that you get for the cumulative flows at A, which is a downstream gauge, must be above the curve that the values that you get for B plus C, which means this curve should be above the 45 degree line. That means that the flows at this point are more than the flows at these locations because of your contributions from the intermediate catchment, if there is no significant water use in the intermediate catchment or if the rainfall is not significantly lower. So, this is what we examine. If this does not happen, let us say that the flow that you are getting here is something of this order. Let us say that you get a curve of this type, which is lower than the 45 degrees. What does that mean? That means that overall the flows at A are smaller than the flows at B plus flows at C, which should indicate that there is some problem with the data, or we are missing the physical picture between physical picture on what is happening between the gauges B and C and the gauge A, what is happening in the intermediate catchment. So, that is what should lead you to see or examine the physical features of this particular catchment. So, that is what we examine in this step. So, if the net runoff in the intermediate catchment, that is accounting for utilization, I keep on saying this because normally we miss these kind of points when we are doing large scale data analysis. You have to also account for utilization. You may have used the water for municipal and industrial supply, and then you have a series that is recorded at a particular gauge. Unless you add this value, add this flow that has been actually extracted from the river, and then you are reckoning the flows at this particular gauge, by adding those, the analysis will not be correct. So, whenever you are doing analysis on the hydrologic data series, you must account for all the upstream utilizations, all the losses, and any disturbance that has taken place in terms of your catchment characteristics and so on. So, if the net runoff in the intervening catchment is added to the outflow at the upstream station, it should equal the flow at the downstream station, obvious. That is, the flow is happening like this, there is a upstream gauge A, downstream gauge B. The flow at the downstream gauge B must be equal to the flow at the upstream gauge A plus whatever has been contributed from the intermediate catchment between B and A, after accounting for any utilization that has taken place between these two gauges. Then the double mass curve is mainly useful in assessing whether the data at a given gauge station is inhomogeneous. That is, whether the data at this station has been affected due to circumstances like in the change like a change in the method of measurement or shift in the location itself, etc. So, we are essentially examining, let us say 50 years of data is available at a particular gauge. You are examining whether this 50 years of data is consistent in a statistical sense with respect to the data that is observed in the immediate upstream gauges. If it is not so, then you have to suspect that the method has been different or the gauge has shifted or that the data is inhomogeneous with respect to the gauges in the other with respect to the other gauges. The double mass curve, however, does not directly indicate whether the data at one station is hydrologically consistent with that at one or more upstream stations. It only shows that there is some problem here, but it may not exactly say that it is in fact inhomogeneous or it is in fact inconsistent. We have to go into exactly what has happened at that particular site. That is what I keep on saying, that physically what has happened in the what has been altered in the catchment is what you have to look at. In many situations, as I will presently show, the double mass curve will be straight up to certain point and then there is a sudden break and then again it becomes a straight, again it becomes a straight line, which means that wherever there is a break, some change has happened in the catchment. Either the gauge has been shifted to a different location and still we are labeling it as the same gauge name, or the method has suddenly changed and therefore, you are able to measure the flows with a better accuracy or in a different manner altogether, and therefore, there is a change in the flow values with respect to the flow values that are recorded elsewhere. Now, while I keep on saying that this has to be a straight line, there will be situations where a non-linear double mass curve can occur, even when the data at two stations are consistent. If the rainfall pattern in the intervening catchment differs from that in the catchment of the upstream location. What I mean by that is, let us say that you have two stream gauges. You take two stream gauges here, this is B and this is A, and when you plot the double mass curve, you expect a straight line, something like this. All right. But you may get a non-linear curve like this. What does this point to? If you have a non-linear curve, let us say this was summation of B and this is summation of A, flows at A. If you get a non-linear curve, it means that the rainfall pattern in this intermediate catchment, which has contributed to the flows at B, is much different from the rainfall pattern which is contributing to the catchment at A, and therefore, you can expect a non-linear relationship. If it is a linear, it means that the rainfall is the same and therefore, you are getting the flows at B as directly proportional to the flows at A, which need not be the case if your rainfall patterns are different. That is what we mean by this statement. Now, the double mask curve is used in the example that I am showing primarily to examine if the algebraic sums of flows at a downstream site with respect to the sums of flows at the upstream gauge site are consistent with each other. So, this is the primary purpose for which we are using especially for this example. Now, I will show you some typical double mask curves. On the x axis, I am showing accumulated sum of monthly flows at immediate upstream gauge sites. So, you may have two gauge sites, you add the two gauge sites flows together and then get the accumulated sums of flows. So, these are flow values, accumulated flow values in thousands of million cubic meters. And we are examining at man-out at one of the gauge sites man-out. So, we plot on the y axis the accumulated monthly flows at man-out in thousands of million cubic meters, and typically you get a straight line. And this straight line is also above the 45 degree line that you may draw, indicating that there is no problem here. Similarly, we draw for various locations, let us say this is Bijore, you may get certain kinks here or certain breaks in the curve, and this may be because of the way you have filled in the data or because of the way the data is being observed, being recorded, and there or because of certain changes that have happened in the catchment. So, these breaks or these discontinuities that you see in the double mask curves point to certain changes that have occurred either in the way of recording or certain physical changes that have happened in the catchment. Now, you see Mandla town with respect to upstream gauges. If you draw a line here 45 degree line, this double mask curve is well below the 45 degree line. Now, this will indicate that there are certain things that are happening in the intermediate catchment in terms of the water utilization, which we have not recorded, or there is also a possibility that the data that is available is so small compared to the upstream gauge data that it has not been able to capture or it is not well representative of the particular catchment itself. In addition, there is also a break here which indicates that some changes have happened in the catchment around this particular time. Like this, the stream the double mask curves will indicate for a particular gauge what has happened with respect to the upstream gauge sites. So, the double mask curve for man-out gauge indicates that the man-out flows are significantly higher than the flows at upstream gauge site. Here, as I said, if you draw a 45 degree line, these flows are much higher compared to all the upstream gauge sites, which indicates that the intermediate catchment flow is much higher compared to the actual observed flows in the upstream catchment, which is possible because the intermediate catchment area itself may be large or the rainfall in the intermediate catchment may be significantly larger than the rainfall in the upstream catchments and so on. Then the double mask curve for Mandla town gauge site indicates a change around 1993. So, this will show that there has been a change here, and we can go back to the data and see where this change is happening, and around 1993 the change has happened, and we can go back to the records and see what kind of changes that have happened here and so on, and then put those changes in some statistical sense into our data. The double mask curve for Bijore gauge site indicates that the flows are significantly higher than the aggregated flows at the upstream sites, implying high intermediate catchment flow. Then the double mask curve for Jamtara indicates a break in the slope and so on. So, the double mask curve essentially indicates whether the data at a particular point, a particular gauge is in fact consistent with the data at the upstream gauge sites, immediate upstream gauge sites, and we get the accumulated flows, accumulated aggregate flows at all these upstream gauge sites and compare them with respect to the flows that are recorded at this particular gauge site. The double mass curve is the first consistency check, first level consistency check that you do when you are whenever you are analyzing large hydrologic systems, such as the one that I showed in this particular example. Then we move on to specific flows, and then make sure that with respect to specific flows also the data is consistent and so on. So, this lecture as well as in the previous lecture I have been emphasizing on the fact that the data that you obtain may be unreliable, may be of poor quality, may have several breaks in the time series, and may in fact be inconsistent with the data that is recorded elsewhere in the same catchment. So, these have to be examined before we start any hydrologic analysis. So, while the stochastic hydrology course we have learnt quite rigorous methods of analysis of the data and drawing inferences from the data, all these methods are only as good as the data that you have for the analysis itself, and therefore, unless you are completely satisfied that the data that you are using is in fact of good quality, is in fact consistent with respect to other gauges or with respect to whatever has happened in the catchment, you should be cautious about making decisions using the rigorous methods that we have studied in this particular course. So, we will continue this discussion in the next class and then complete the data consistency analysis, and also perhaps look at how we account for the control structures, which means that there is a reservoir which has been operating for several years, and then you are recording the flows downstream of the reservoir. But for analysis purposes you need naturalized flows, and how do we convert this controlled flow sequence into a naturalized flow sequence, which only should be used in the analysis. So, we will continue this discussion in the next class. Thank you for your attention.